Hey, check it out. It's a biology book. Are there any forces on this biology book? Well, if it's near the surface of the Earth, there has got to be a downwards force of gravity on this biology book. But how do we figure out how many newtons of force this would be? Well, the gravitational force is the best. It's the easiest. I love the gravitational force. It's just m times g. That's the formula for the magnitude of the gravitational force. What is m? M is the mass of the object that's experiencing the force, and so in this case, it's the biology book. Let's say it's a 2 kilogram biology book. And g is the magnitude of the acceleration due to gravity near the biology book. That's a mouthful, but you already know this. The magnitude of the acceleration due to gravity near the surface of the Earth, which this biology book is probably near the surface of the Earth. I don't know why it wouldn't be near the surface of the Earth. It's just positive 9.8 meters per second squared. That's what little g is. So to find the gravitational force, really easy. It's going to be 2 kilograms, the mass of the book, times positive 9.8 meters per second squared, which gives you a gravitational force of 19.6 newtons straight down. So 19.6 is the magnitude of the force, and the direction is straight down. And if that was the only force on this book, it would plummet straight downward, accelerating and striking the Earth. But let's say there was a table beneath the book, and we set this biology book down on the table. Is there still a force of gravity on this biology book? Heck yeah, there is. You can't fool gravity. Gravity's still straight downward. It's still equal to mg. It would still be exactly 19.6 newtons straight down if this biology book is still 2 kilograms. Are there any other forces on the biology book? Turns out there is. A lot of people don't like this. There's a normal force on this biology book, and it points straight up. The table is exerting an upwards force. We call it the normal force. And it's a force that points perpendicular to the surface. So this is pointing out of the table, perpendicular to the surface of the table. People don't like this so much. People say, no. Table's not exerting any force up. The table's just in the way. You've got gravity down and the table's in the way. That's why the biology book doesn't move. But it doesn't work like that. If there's a force down and no force up, if this gravitational force downward is unbalanced, this biology book would have to be accelerating downward. It would have to either move through the table or crush through the table, and that's not happening. The biology book is just sitting there on the table. That means the forces have to be balanced. There has to be a normal force outward. But people find this hard to believe. They're like, how can a table, just an inanimate object, ever cause a normal force outward? They believe, a lot of times they're able to believe that, well, if this book slides on the table, there would be a frictional force, and that frictional force would point parallel to the table. But the idea of a normal force pointing out bugs a lot of people. I mean, how does the table decide how much normal force to push with? If I were to put a 4 kilogram biology book on the table, the normal force would have to be bigger. It'd have to be twice as big. But how does this table know to push twice as much? This is weird. It's an inanimate object. How does it decide how much to push? Well, essentially the table, or any other surface, decides how much normal force to exert based on the amount that the surface is compressed, bent, or bowed. Imagine walking on springs. The springs will exert more force for a heavier person since the springs will get compressed more, and they'll exert less force on a lighter person because the springs will compress less. Now, this table is not made out of springs, but if you put a heavy enough book on it, or people, lots of people standing on each other, this table would start to bow downward. You'd notice this thing is changing its shape. And the table does not want to change its shape, because if you take those people off, this table restores itself to the horizontal position. And it's this restoring force, the fact that this table does not want to get bent out of shape, that this table wants to bring itself back into its proper orientation, that gives rise to the normal force, the fact that this table does not want to get compressed. And that's how the normal force decides how much to push with. If you put heavier things on this table, it'll bow more, it'll compress more, the book will compress more. It might be hard to see, but it's getting compressed. And the more it's compressed, the more it's trying to restore itself back into its proper position and orientation and shape. Alright, hopefully I convinced you that this normal force is cool, it's okay to have, and by the way, it's not called the natural force. I hear it called the natural force. There's no natural force, this is the normal force. You might wonder, why is it called normal? Is that like a boring force? Is that what that means? That's not what we mean by normal. What we mean by normal here is the mathematical sense of perpendicular. So a normal line, a perpendicular line. This normal force is perpendicular to the surface. It's always perpendicular to the surface exerting it. But what's the formula for normal force? Yeah, about that. There is no actual neat formula that always works for normal force. Turns out you just have to use Newton's second law in the direction that the normal force is in, and you just have to solve for the normal force based on the information you know. What does that mean? Well, for instance, Newton's second law for the vertical direction looks a little something like this. Acceleration in the vertical direction would be the net force in the vertical direction divided by the mass. For this biology book, what is the vertical acceleration? If it's just sitting there, there's no vertical acceleration, it's just sitting there. So this would be 0 equals the net force vertically. Well, I've got Fn upwards. So I'm going to stick that here, and that's going to be positive because it's upward, and I'm going to treat up as positive, minus the force of gravity is down, mg, but I already solved for that, so 19.6 is downwards, divided by the mass was 2 kilograms. Turns out it doesn't matter because I can multiply both sides by 2. 0 times 2 is still 0, equals Fn minus 19.6 newtons. And if I solve for Fn, I get that it's just 19.6 newtons. What's going on here? Well, this had to be like this. If the biology book is not moving, it's not accelerating, that means the forces are balanced in the vertical direction. That means the normal force just has to be equal to the gravitational force. That actually makes sense. So is it always equal to the gravitational force? Not always. A lot of times it will be. If the object's on a flat horizontal surface and there's no extra vertical forces and there's no vertical acceleration happening, then yeah, the normal force will just be equal to mg, just like gravity, because it has to cancel mg. But if there's an extra force on this object, maybe someone's pushing down with an extra 10 newtons, I'm mad at my biology book and I'm pushing it down because I'm trying to punish it, then what would the normal force be? So what would change over here? Well, I'd have an extra 10 newtons downward. That's down, so it's going to be minus 10 newtons down, which means over here I'd have minus 10 newtons down. And when I solve for this, I'm going to get that Fn equals 29.6 newtons. So the normal force isn't always equal to mg. If there's an extra vertical force, you've got to factor that in to the Newton's second law and then solve for the normal force. Also, what would happen, you might ask, if we stuck this whole thing in an elevator? I do that all the time. Let's say it's in an elevator going up. It's accelerating up with 2 meters per second squared. Then what happens? What changes over here? If I'm still in this elevator pushing down with 10 newtons on the biology book and the whole thing's going up with an acceleration upwards of 2 meters per second squared, well, our acceleration just wouldn't be 0. Our acceleration would be 2 meters per second squared. I'd have to multiply by this 2. That means this side would be 4, and it'd have units of newtons. I'd solve for this normal force. It would then be 4 plus all of this, which would give me 33.6 newtons. So long story short, gravitational force always equal to mg. It's lovely. I love the gravitational force, which, by the way, is also the weight of the object. Weight is the exact same thing as gravitational force. And it is not the exact same thing as mass. People mix up weight and mass all the time. We use them interchangeably, but the weight does not equal the mass. Weight is equal to mg, in this case, 19.6 newtons. Mass is equal to m, in this case, 2 kilograms. Does 2 kilograms equal 19.6 newtons? No, not really. These are different things. The weight of 2 kilograms is 19.6 newtons, but don't mix these up. These are not the exact same thing. And the normal force is the perpendicular force exerted by a surface. It exerts that force because it's bending that surface more. There's no formula for it. A lot of times it's also equal to mg, but if there's extra forces vertically, or acceleration vertically, or if this was not on a horizontal surface, you'd have to just use Newton's second law and solve for what the normal force was.